Welcome to an introduction to generative AI art and robotics art. This is an introduction to the Creative Machine exhibition taking place at Taikang Art Museum, provided by the Creative Machine Group and London Geometry in London. Hello, I'm Frederic Fol Leymarie. I'm also a professor at Goldsmiths, University of London, and today I have the pleasure of being with you and will walk you through a description, an overview of what you may expect in the exhibition. So let me tell you a little more about what's coming up. We will have some details on AI of today, mainly based on a look at what artificial neural networks can provide to us. We'll also look at some examples of using machines and so-called robotics, more evolved types of machines controlled by computers, and how these new technologies are used in the world of art, artistic creation. We will have examples later on during the presentation of using some specific types of ANNs, or artificial neural networks. So in particular, we'll see examples with using GAN, generative adversarial networks. We'll see examples of using diffusion models. We'll see examples of modeling evolution as we find it in nature. So that approach is also used by artists and in sophisticated softwares. We'll talk a little bit about what's happening in recent years in AI. We have the notion of foundation models, so we'll say a few words about that. We'll also see some sophisticated computer simulations where we have dynamical experiences with some notions of physics that's simulated. And this is all used by different artists, as we will see through the presentation. We'll also have some example of robotics and art. And on the right side here on the slide, you see a sort of a classification of the different types of artificial neural networks architectures and different types of robots that we will see some examples. Things like plotters, more simpler type of machines. The most sophisticated today would be humanoid robots, robots that resemble humans in their movements, in their capacities. Also, simpler type, sort of intermediate between plotters and humanoid robots, or robotic arms, mobile robots that can move on large surfaces and create very large artistic renditions. We also touch upon the world of virtual reality, and we'll have some examples in the exhibition. So let me give you now a brief overview of what we mean by artificial neural networks, or shortly called ANNs. And later we'll see potential impacts, especially in the world of artistic creation. So more generally speaking, artificial intelligence as a field of research and applications includes many subtopics and subdisciplines. What we hear a lot these days in the media, for example, is what's called machine learning applications. So it's a subset of what artificial intelligence is about. And machine learning, as the name says, it is about methods so that, provided to machines or software systems so that they can learn. And they can learn mainly from looking at lots and lots of examples, so-called data. In the world of machine learning, there are many types of techniques. So there are smaller subsets, and an important subset of machine learning in the last, let's say, 15 years especially, is the progress made on artificial neural networks. So these systems are meant to learn from data, but they represent one important type of machine learning approaches. So just be aware that there are other techniques, and those could be used as well in the context of robotics and could be used by artists. But in this exhibition, we'll focus mostly on artificial neural networks and their use. And in the recent years, what has made artificial neural networks successful or more successful than in the past is the introduction of a progress in those technologies, so-called deep learning. Essentially, this means that you're looking at rather sophisticated artificial neural networks architecture. And as we see on the bottom right of the image, we see a notion of multiple hidden layers. So basically you have a stack of lots and lots of so-called artificial neurons. These are devices in a computer system which capture a piece of information based on an analysis of data. And as you may guess from the picture, these artificial neurons individually are connected to other ones. And they tend to be connected within a layer, here shown as a column. And then they're also connected to other layers or other neurons sitting in other columns. And the more layers you have, the deeper, we say, the system goes, and hence the name deep learning. There is some analogy to make between artificial neural networks and biological neurons. So the initial idea of an artificial neural network, which is essentially a system that takes many pieces of data, analyzes them, does some computation, combines them, which is what you see here in the middle, combines them, then applies some function, some reasoning, some methods on the pieces of data, and then creates an output. And this neuron, which is essentially one of these green circles here, then can be connected to another set of neurons which look like this little piece here. And here on the left you have a very simplified diagram of what's happening in biology, what we know exists in our brains and in our bodies. We have let's say biological neural networks, and in the brain in particular we have this structure that we see here, so-called neurons. So you have sort of a central cell, you have an axon and dendrites, extremities, sitting on either as sort of input to the cell and then an output of the cell. And one of the differences with artificial networks is that the number of connections either coming inside the cell or coming outside the cell is vastly superior to what we see in artificial neural networks. So for example, it would be typical for a neuron to receive inputs from 1,000 different other cells. Also in the case of the human brain, or other animal brains, there's a lot of interactions, and the complexity of the network, how these cells are connected to other ones, is very, very complicated. And we're still studying and trying to understand how the connectivity functions and what type of functions these networks, these biological networks might perform. So what we see here in the context of computers on the right is really a simplification. Nevertheless, such systems have, in let's say the last decade or so, have become quite powerful and quite useful in a number of applications. And we will see by looking briefly at the history of the use of computer and software and robots in art, that neural networks are now also explored and used by current modern contemporary artists. But before we look at the very recent work, we want to give you an idea of what are the origins of so-called computer and art and robotics and art. So we'll look at some of the early works and pioneers in that field. And in the exhibition, you will see many of these examples on display as well. So here's an example of a mid-century, last century artist, Heinrich Heidersberger, known as a photographer mainly, was engaging with technologies of the day, as you may sort of guess from these pictures. And he's an example, early example, just prior to the era of computing, of an artist who wants to explore their art practice through technologies of the day, of course. So this is 1955, which is actually an important year for the history of artificial intelligence. It is in 1955 that the word artificial intelligence was created, and the following year was the first important conference where different scientists met and set sort of a set of objectives for the field to be concerned with. And if you look at the details of that meeting, that conference, at the time, the scientists are trying to elaborate a program of research which focuses on the human intelligence and how could this be understood and perhaps duplicated via computer systems. And thus, in those years that follow, especially since the early 1960s, when computers become available beyond just the advanced research labs and are now present on most university campuses, at least in some of the universities around the world, you see, of course, other young artists who are curious and want to engage with these new technologies, new ideas, and apply them to an artistic practice. So here, for example, you have two important persons named Herbert Frank from Austria, computer scientist who will engage in computer art via computer graphics and will be one of the early contributors to software for computer graphics. He's also well known as the co-founder of Ars Electronica, a major center in Linz in Austria for technology and art, and in particular computer and art and robotics and art. It's a center you can visit. I invite you, if you're ever in Austria, in Linz. There's a permanent exhibition, a very nice building, and they also have events through the year. Harold Cohen is another very important artist in conjunction with AI and robotics. A British artist, well known in the 60s, having already an exhibition, early exhibition at the Tate Modern, the major modern music art of modern art, in England. And in the late 60s, early 70s, he discovers the potential of computers and robots. And through the rest of his career, until his unfortunate death a few years ago, he will develop sophisticated AI and robotic system called Aaron, which is now recognized as the most sophisticated and early example of AI art and robotics from that period, from the 70s until recent years. We will have examples of art produced by these two important persons in the exhibition. And here's a sort of overview of many names of artists from different period engaging in different ways with computers, robotics, different types of softwares, different types of mathematics. So, for example, if you look at the middle top, you see Conway and Mandelbrot, two mathematicians who will engage with particular type of approach called fractal geometry. A new way from the 1960s and 70s in mathematics this time to describe complex, complicated structures, objects that, for example, we can find in nature. So, for example, things like plants, forests, flowers, things like landscapes, mountainscapes, things like waves with all the details. So they are exploring how to apply new ideas in math and create beautiful, interesting artistic renditions. Harold Cohen is considered to be a pioneer in exploring symbolic, so-called symbolic AI. So this is a type of AI different from the use of neural networks, where instead a sort of expert system, a system which has lots and lots of knowledge and rules, such that if it encounters a particular situation, it will apply a particular set of rules. And this is the idea that humans have over time learned a number of such similar rules, and we're trying to simulate that kind of approach here. And Harold Cohen will develop, again, one of the most sophisticated systems from the 1970s and on, based on that idea. Many other artists engage with software ideas and algorithms, and you have some names in the middle here. We'll encounter them again later in the presentation. At the bottom, you see the appearance of evolutionary art. So this is the idea again that evolution, as we find in nature, which creates all these wonderful, so different types of life forms, if we could understand it and simulate it, we might use it to create new forms. And this has been studied by scientists, of course, but also by artists who take those ideas and make them unique in their practice. And we'll see some examples later on. At the very bottom, you see a few names here of current artists who are exploring especially the more recent types of artificial intelligence systems. So we'll move on and see examples as we go along. So in terms of historical perspective, here's one of the pioneers, important pioneer, German, again, Friedrich Nacke, still alive, still practicing nowadays. And you have some examples from the 1960s now of explorations with computer systems and printers, or so-called plotters. So here you have a conjunction of using software to drive machines that create real printed, or using brushes with ink, for example. So real material pieces are created on canvas, as you would do with your hand, but here the artist is using the machine as an extension of their body. Herbert Frank, we've mentioned before, using here some examples, early examples of his work using computer systems. So you have renditions of geometric patterns, often use more a type of abstract art approach or practice on the left. And on the right, you have the use of filters of the days. You could think of filters you find on your mobile phone these days, or using a tool like Photoshop, how to modify an image and create interesting shapes and forms. So these are concerns that the artists of the day in the 1970s are already exploring. Vera Molnar, another very important artist of that time, who has an entire career since the 60s and here 70s, represent also an approach which is more on the abstract side, and thinking of ideas from geometry and creating new types of renditions using the power of software and plotters or machines. And here's some other examples. There are many important pioneers. Here you have some of other important names, and notice that Ernest Edmonds and Paul Brown are still active today, very much active, in fact. And I invite you to visit their websites. Just Google their names or search for their names, and you'll see all kinds of wonderful explorations. And some of them will be in the exhibition. Other types of productions, this time a bit more recent. We see the appearance of 3D renditions as computers of the late 70s, early 80s starts to be able to produce interesting forms in 3D, 3 dimensions. And also we see more sophisticated textures and colors appearing. So again, the artists exploring technologies are often the first, or some of the first, to look at the possibilities offered by the latest technologies developed here in the sense of computer graphics. Harold Cohen, we mentioned before, and here a return on some of his productions. So these productions are in collaboration with the sophisticated AI and robotic system he developed called Aaron. And you have works at the top which represent drawings created by the machines, and at the bottom you have colored versions of these drawings. So if you look at the history of how the work of Harold Cohen developed, in the early phases, so early 80s, about those dates you see here, the color schemes and the coloring is done by the human artist. Later, through the late 80s, early 90s, Harold Cohen will figure out a symbolic AI approach, an approach where you have rules to give the machines a similar power, a similar quality of selecting colors and adding these colors, these paint to the drawings that the machines can produce. Very interesting work. I recommend looking at his work in more details. There are books published about his career. A return this time on more the sort of influence of mathematics. We mentioned Benoit Mandelbrot, John Conway before. Mandelbrot, famous for introducing the concept of fractal and fractal geometry, fractal theory. And you see one particular example on the slide here. And a fractal has basically very sophisticated shapes, sophisticated geometry at many, many scales. So if I were to zoom in this area, I would see very sophisticated, complex structures of that scale appearing even at the tiny, tiny scales. John Conway, famous for many types of contributions in mathematics and software, computer science, but also famous for introducing the concept of the game of life. Essentially a rule-based system, so a bit like what Harold Cohen was using, what we call symbolic AI, where the rules generate patterns which evolve through time. And as they encounter other patterns on the screen, so imagine these pixel forms here are actually moving in their neighborhood, and when they encounter other objects nearby, new rules are enacted and the shapes of these objects keep changing. And it's what's interesting here is that as you modify the parameters, the rules, unexpected events occur, unexpected forms are created. Hence the name Game of Life as a very early approximation of how shapes in nature might appear, or at least the idea of sophisticated shapes appearing in nature is embodied in these approaches. William Latham, who is co-curator of this exhibition and will be present at the opening of the exhibition, is also one of the early pioneers, and he was in particular influenced by evolution, the idea of evolution in biology. The history goes that when he was a young student in the 1980s in London, he would go to the museum, the Natural History Museum, where he would see all these incredible shapes of all kinds, plants, animals of all types, small creatures, huge creatures. And he got inspired by this idea of evolution to try to come up with a set of rules. So again, think of a symbolic AI approach, but in the context of simulating evolution in nature. So in evolution, you also have not only the possibility of putting different complex shapes together. Imagine cells that get together and create more and more complicated forms. But you have ideas of a code, the DNA that we have in each of our cells, a code which encodes possibilities for each cell and how they might combine. But DNA can also be modified. It can be modified by having parents joining their code and creating children. It can be modified by mutations, some random changes to the code. So these ideas have been simulated in the systems that William Latham was producing back in those days. So what you see here is hand drawings of examples derived from these rule-based systems. But later on, in the late 80s, William Latham will join the IBM Research Center in Winchester, near London, and with computer scientists will implement a computer version of this approach. Manfred Mohr, another important artist of that period from the 60s, 70s up till now, is still active artist. So another example of creation of mostly abstract art, explores also the use of colors in his art, and use actual prints the art via different systems, different machines. And so we will have some examples in the exhibition. After this overview of the early works by pioneers, we're now entering the modern era, more or less the last decade or so. And we will look at different uses of current AI technology in the context of using artificial neural networks and modern simulation of evolution, as well as sophisticated simulation, dynamic simulation with some approximation of physics. Be aware that in this exhibition, we're only covering some of the current progress in AI. So here's an example from a website. You have the link at the bottom, so-called neural network zoo. A zoo in the sense that there are so many possibilities of building artificial neural networks. And here you just have a glimpse, some of them that have been explored in the last few decades. And many of them have been developed much more recently, in the last 1 or 2 decades. And there are more. This is just a snapshot. I invite you to visit that website. And that website will perhaps not show even the very, very recent approaches, such as so-called transformers, which are more sophisticated versions from architectures that you can find on that description there. You see interesting names like Hopfield networks and Boltzmann machines, which recently, the type of work that was recognized by Nobel Prizes in physics. So these systems are having impact in many, many different fields. You can learn about problems from data and apply them to many fields: mathematics, physics, chemistry, and graphics, and media, and the world of art. In the very recent years, some of these architectures are being described as foundation models. What's a foundation model? A foundation model is a type of neural network, so a particular architecture, but one which is adapted and trained with data and information on the data, which is of very many different natures. So data where you have image type data, data where you have text, data you may have sound or voice, video, and all these types can be combined. When they're combined and when the architecture can make sense of relationships between these very different types of data and then be applied to practical problems, we call such a system a foundation model, a model that can be used across many types of applications, hence the word foundation. And we can then refine a particular foundation model by adding some training in a particular context and benefit from the base, the foundation that was already there, so that we don't have to spend a lot of additional resources to make the system do something useful for us. An example that is well known these days of such a foundation model is the so-called GPT series of systems from a company in the USA called OpenAI, but there are many other such systems, including in some developed in China and in Europe and elsewhere in the world. Some of these systems are mostly used in the context of language, so the human will have a conversation with the system, and the system will either produce some response in terms of text, but could also produce response in terms of imagery, etc. Some systems are more focused on imagery and video and sound, and some are focused on graphics and designs. And of course, some of these systems are used by artists. So for example, in the exhibition, we'll see examples by Parashkev-Nachev and Memo Akten. Parashkev-Nachev, Dr. and Professor Parashkev-Nachev, is an expert in neuroscience at UCL in London. And he's also an artist and has been exploring forms of artistic rendering using technology for many years. And here's a sort of a snapshot of so-called canonical portrait series, where he combines data from many, many different sources and create types of representations in the form of a portraiture. And as you invite you to come to the exhibition, and you will learn more about the meaning and the approach of Parashkev-Nachev. One very popular type of architecture used in the recent years is the so-called GAN, or Generative Adversarial Networks. Here you have a sort of summary on the left here of the architectural structure. So what's specific about the GAN is that you have two networks, two artificial main networks, so-called generator. So this is a network that takes some input, could be random noise, and has been trained on lots of examples before and used this input to create a potential outcome, here illustrated as an image, a sort of calligraphic image here. And there's another network which is looking at those productions by the first network. We call it a discriminator. And that network is trained to say, how good is this outcome? And good here means, is this outcome something that corresponds to a real outcome, or is it fake? essentially the discriminator is criticizing the creation by the generator and is trying to tell the generator, well, what you've done is really the result of a machine. It doesn't correspond to a real calligraphic trace as produced by a human. And the generator will take that into account and then modify a little bit its learning and try to improve. And this sort of discussion between the two systems will go on and on. The generator will start producing better images, better outcomes, and the discriminator will have to learn at the level of details whether this is believable as a real possible outcome or not. So the discriminator will also change its learning. And this conversation keeps going on and on. And as it goes, the outcomes tend to get more and more interesting. And this approach has been used for many years now, I would say in the last 10 years or so, by artists, contemporary artists. A good example in the exhibition is from Memo Acten. Also note this particular picture here is a picture of an outcome of such a system, which was produced a few years ago and has made a name for itself because it was sold at Christie's and sold for a very significant amount. So here you see in pounds, in British pounds, over 400,000 pounds. So this was sort of a first for a piece of art which was created via a AI system. Of course, behind that there's a group of human artists called Obvious Collective, and they are selecting and adjusting the parameters of these systems. So this is really a collaboration, human-machine. Memo Acten, we just mentioned, and these are examples of the type of works you'll see in the exhibition. So this particular work is from 2018. Memo has been active for many, many years. He's explored different types of technologies, video processing, photography, mixed with computer software. And in recent years, he's engaging with the most sophisticated softwares approach from the world of AI. And this is this particular piece, which you can find by searching on the internet, illustrates the use of generative adversarial networks, which we just described, and also another type of architecture called variational autoencoders. Other works by Memo, again, Memo Acten. Memo did his PhD at Goldsmith in our group, so we're very familiar with this work and explorations. Diffusion models, another type of approach, very successful in recent years. It's an approach that allows to produce photorealistic outcomes. So here, for example, you see that it's trained and producing outcomes on the right, which resemble different types of painting, different styles. The idea in diffusion models, very briefly, is that the architecture is actually learning about a noise that is added to the initial data and that slowly basically brings the original data to a fully random set of final image. But the system is basically learning about what happens to the original images during the training phase when we add particular so-called diffusion noise to these data sets. So it's really learning about undoing. If I try to reverse the process, what I've learned about how the noise is changing the data, I can actually inverse that process. And this has been shown to be a very successful approach. So the system, once trained with sufficiently amount of data, will inverse the process. And so here's an example, again, by Memo Acten, using this kind of technique and producing particular types of, here, almost impossible imagery in the middle of a tempest in an ocean somewhere, a virtual scenario, but looks excellent and almost photorealistic. Now we will look briefly at another category of modern practice in art and technology that we've briefly mentioned before, the so-called evolutionary art and artificial life type of approaches. So these are approaches which are directly inspired by biology and especially evolution. The idea of evolution, that all living species, whether they're plants, mushrooms, bacteria, humans, other animals, we all have inside our cells, individual cells, trillions of cells that make our body. We have this code, this DNA. And that code can be modified, and it leads to the next generation, our children, and in the future, the species may even change and become a different type of species. So these ideas have been used by some artists and incorporated in software, and we'll see a few examples. So William Latham, we mentioned before, developed in the late 1980s, early 1990s, a computational version of his symbolic AI system, rule-based system, to create life forms that have an organic sense. And on the right here, you see an example from early 1990s, produced by a set of computer systems developed in collaboration with computer scientists, one in particular called Stephen Todd, that is still working with William Latham today. And the system is called Mutator, so you see a direct inspiration from evolution in biology and the concept of mutation. And here you have the result after many, many, many iterations or generations, where the artist would start with very simple forms, and using the simulation of evolution would see these forms change over time, grow, be combined. The artist would interfere with the evolution. You can think of the artist as sort of acting as an agent of mutation, selecting based on the aesthetic value that the artist sees in the forms. So there's a notion of aesthetics that appears and that is conducted by the human artist in this case, while the software is generating all these complex figures. So this is, by the way, this is a fully 3D volumetric outcomes. You can slice through the object, and inside there is also information. There's also sophisticated outcomes. So it is, again, a simulation of life as it might be on a computer. In the exhibition, we'll see more recent work by the artist William Latham and his team. And this particular work builds from the previous one that we described from the early 90s, but has been revisited. You will experience it on a very large screen, and it is interactive. It has notions of physics. These forms are animated, but they react to you, to your own movements. I invite you to come to the exhibition and experience this art. Here's also another piece of work, which is very sophisticated drawing. So this is a physical outcome coming out of the software technology. Recent developments by William Latham and his team. And here on the right, you see another example, which is a piece of work using similar systems by Latham, but that would be experienced in the context of virtual reality. Other modern artists exploring technologies through software, and also through, in this case, Andy Lomas, through 3D printing. So Lomas has developed sophisticated software where forms can be evolved. So again, this notion of inspiration from biology. But eventually, when the artist is satisfied with the outcome, will decide to create a 3D sculpture of of the outcome. Very interesting work by Andy Lomas. Andy Lomas had a previous career before he engaged fully with his art practice as a computer graphics expert, and he worked on production of many well-known movies in the 90s and 2000s. So very aware of what can be done with sophisticated computer graphics. Carl Sims, also on display in the exhibition. Famous scientist, early 90s at MIT in Boston, in Cambridge, Massachusetts, at the celebrated engineering university there. Carl Sims explored also the potential of evolution in software, and you see some examples here. And he's also famous for having created a simulation system of 3D forms that evolve through time, through computer time, and change their shapes and find ways to occupy the environment. And so I invite you to research this work from the early 90s. It's extremely interesting and well ahead of its time. Carl Sims then had a career in special effects in computer graphics, a bit like Andy Lomas, and more recently has taken a break from that type of work and rejoined his artistic practice. So there is recent work by Carl Sims, some of which will be shown in the exhibition. Maxim Zetskov, originally from Russia, now based in London, is a more younger artist, engaging again with sophisticated technologies of the day, and he's well known for his work in grandiose and fantastic simulations using physics of dynamic works that keep changing over time. So it's a good example of that type of approach through the work of Maxim. And you'll have some examples in the exhibition. Maxim more recently is also engaging with virtual reality as another medium. He's also currently working in the world of computer games. I invite you again to look him up. Great work coming out of his practice. So now we are at the final part of our overview of current developments in art and technologies, and examples that will be shown in the exhibition at Taikang Art Museum. We will see some examples, early examples, and then move on to more recent ones, including in this section some examples of the use of virtual reality and related approaches. So early on, going back to the pioneers, here you have two important artists we've mentioned before, using machines to render the final examples of the art produced. On the left, you have an example of abstract art with a plotter by Manfred Moore. And on the right, you have an example of a machine created by Harold Cohen called Aaron, which here is from the 1980s, where the system has evolved and now can actually paint and put color directly on the canvas. And this canvas can be very large. In the exhibition, we will have physical systems from modern artists, current artists. So here's a first example here by Felix Luc Sanchez from Spain, who now has moved his studio in Belgium, in Brussels. And Felix looks at the combination of technologies from AI, from other type of software computing approaches, and also engages by building machines, looking at different aspects of physics here. This particular piece will be on display at the exhibition. It is human scale. It's very impressive. In the VR world, we have again a long history. We can go back at least to the 1980s. And here are two pioneers, Charles Davis and Rebecca Allen. There's a rich history. You have some links. But again, search for art and virtual reality, and you'll see that from the very origin of concepts of virtual reality be essentially the idea of immersion. How can we go from simple screen-based visualization to be immersed in the virtual data? And this is done visually and also using sound. And in more modern systems, we start seeing systems which give you a sense of touch, pressure on your body. So again, there's a rich history, and here are two examples. But in the exhibition, we'll have some current work, some current approach. So in particular, artists from China, Yazhou and Han, will have work. And please enjoy the work and explore the work in the exhibition. In terms, going back to robots, very recently developed the practice of Patrick Tresset from the last decade. Patrick builds his own robots. There'll be examples similar to the ones you see in these images in the exhibition. Patrick has done a lot of work on portraiture. You have an example here on the left. Patrick was a practicing artist, exploring various types of styles in painting, in drawing, abstract, photorealistic type as well, portraiture. And in the mid-2000s, late 2000s, he came to London. He was at Goldsmith. We worked together. And he started to explore the potential of software. And then a few years later, around 2010, he started to engage with robotics. And what's particular about his practice, his approaches, he builds his own robots. Each robot has some individuality, some particular characteristics, and will create drawings or paintings which are unique. In some performances, he will have many such robots. Here, you have a snapshot of an example of a school of robots with a teacher at the front who's indicating to the art class what they should work on. Again, a sort of scenario that you will experience in the exhibition. And just before concluding, let's look at an actual example with a video. So what you're going to see here is one of the robot called Paul, a series of robots called Paul, developed by Patrick Tresset, French artist, had his studio in London for a while, and now is also in Brussels in Belgium. And the robot is essentially an arm which has the possibility to manipulate a pen or a brush in a way of the arm of a human. So it moves in a similar way. It also has an eye. You see the eye here. A camera-based system which can observe the drawing and actually tell the arm what to draw next. So there's an interesting feedback going on here. So here the artist is first giving an initial set of lines, drawing to the robotic system. The robotic system observes what is being already done and then goes on and completes or adds their own signature, their own style to the drawing here of a portrait of a face, of a human face. Oh, of course, this is accelerated. The robot will move at a speed which is similar to a human. So this would take many minutes, maybe 10, 15 minutes to complete. And finally, the robot will sign the piece. This very interesting example where you have a notion of feedback. And the feedback is performed using some recent technology from the world of AI. There is documentation. Patrick sometimes publishes work, this description of his work, so you can find some description of how this might be done. And to finalize our presentation today, I wanted to give you also an example of a humanoid robot. So this is a robot which resembles more the body of a human. In this case, it's a Baxter humanoid robot from a few years ago. And this is work I've been involved in collaboration with the Italian artist Daniel Berio and in collaboration with roboticist and machine learning expert Sylvain Calinon in Switzerland. And this robot learns from its errors and is doing sort of calligraphy type of art. And in this particular video, the robot will improve on its calligraphic style and eventually be able to create a calligraphic rendition of its own name. You see that the robot can work in collaboration with the human. It responded to the movements of the human. If it encounters an obstacle like a human body, it would stop moving. So this is a very nice robot to work with. And you see here that it's learning to improve by reaching different targets. It's learning how to draw letters in a particular style. We call that a graffiti style. So here it's practicing an E and then an R. These are the basic letters to create eventually its own name. So underlying this system is some learning mechanisms. So we're talking about machine learning approach, as we discussed very early on in the presentation. Finally, the robot is able to create a full calligraphic rendition of their name. Observe that the speed and the movements are very similar to what a human would do. Of course, we can do other types of renditions. So, for example, we can draw in thin air. And this is sort of exploratory and the team having fun with the robotic system. Here's a teapot flying in thin air. And you have all the people involved. So, we're at the end of our journey, our brief journey through an introduction to the Creative Machine exhibition at Taikang Art Museum in Beijing, opening mid-November 2024. Thank you, and I hope to see you at the exhibition.